Okay, thank you very much. So thanks for the introduction, and thanks especially to all of the organizers. I was disappointed that I didn't have a chance to visit God's own country due to the pandemic, but I'm very glad that the conference could be arranged so that we could all do this from safety. Okay, can everybody hear me and see my slides okay? Is this fine?
Yes.
Okay, great. Okay, so I want to talk about an upper bound for counting number of fields, but I know the audience for this talk is very diverse, and so mostly I want to give a summary of the question of counting number of fields, which is a very active field of work. Part of arithmetic statistics, as it's commonly known. And so I want to sort of introduce the question, the basic conjecture, and then I want to say a little bit about the various methods that are currently being developed to study this problem. So by the time I get to our proof, which is joint work with Robert Lemke Oliver, probably by that point I'll be out of time, but that's okay, because mostly I want to introduce the question. Okay, and so here it is. Here's the question: is how many number fields are there? Well, you can quickly, so a number field just being a finite degree extension of Q, and you can quickly convince yourself that there are infinitely many. And so one counts by degree and discriminant, so which are the two natural invariants by which to count these. Okay, so let's introduce a little bit of notation. So we're going to write nd of x to be the number of degree d number fields whose discriminant is bounded above by x. And it's also very common to count by Galois group. So it turns out that many of the methods, not all, but many of them work most effectively if you work with one particular Galois group at a time. And so the Galois group, so we're not necessarily counting number fields which are Galois, and so the Galois group here refers to the Galois closure of any number field k that's being counted. Okay. So the two classical results in this subject. So Schmidt proved that for each fixed degree, the number of number fields of bounded discriminant is finite. And then Minkowski proved, as part of his theory of the geometry of numbers, that for a degree d number field, you have this lower bound on the discriminant of k, which is turns out to be exponential in k. And this is believed to still be approximately sharp. Well, it is approximately sharp. So one has found infinite class field towers so that the discriminant is a fixed constant to the degree of the field. And this is part of a course in algebraic number theory. For example, this is how one proves that there are no non-trivial number fields that are unramified everywhere. Okay, so these are the first results in the subject, and here's a result we would very much like to prove, is that for every degree d and every Galois group that's transitive, that can occur as a Galois group of a degree d number field, well, every Galois group that can occur does occur, is the conjecture. And this is very much unproved, right? So you prove this, you get famous. Okay, so as I heard in one of the talks yesterday, if you don't know how to solve a problem, then make it harder. And so here we have the following conjecture of Malle. So rather than just saying that ndxg is non-zero, that there is at least one number field, of every degree and allowable Galois group. So Malle predicted the asymptotics for this, where these constants A and B are explicitly described in his paper. A is fairly simple to describe, B is a little bit more involved, and the constant C is in general complicated. And what we know so far, we don't believe that there are, there's probably not a nice general formula for C of G, but for A and B there are. And so this is the game, this is the question. We want to understand this quantity, we want to count number of fields, and what can we say? In what cases can we prove this asymptotic? In what cases can we prove lower or upper bounds? Basically, any progress towards this question is interesting. Okay, and I want to sort of give a whirlwind tour, a very brief overview of 4 general types of methods which are seeing active work. So first of all, what I'm going to call generator methods due to Schmidt and Ellenberg and Venkatesh. So I'm going to explain to you Schmidt's proof in this talk, but this is also the umbrella that our main theorem falls under. And basically, you count number of fields in terms of their algebraic integers. So this is the most general of all the methods that I'm going to talk about. It applies for every degree and every Galois group, but we're seeking upper bounds. So it seems very unlikely we're going to get any sort of asymptotics this way, but we can prove upper bounds. Okay, so there are Abelian methods. So in case you're counting Abelian extensions, there are methods which are very effective at that. Okay, and so, of course, Abelian Galois groups, this is a very limited case, but in this particular case, we can do quite well. Okay, so there are parametrization methods due to, well, many people, but Davenport and Heilbronn in the case of cubic words, cubic fields, and Barkova in the case of quartic and quintic fields. So if you're familiar with Barkova's famous and really brilliant work, this is, this falls under the umbrella of the so-called higher composition laws. I'm going to sort of say very briefly about that. But basically, you're counting lattice points, and so you convert this into a question in analytic number theory, and these are in pre-homogeneous or sometimes co-regular representations. So basically, what one has to do, so it's known from invariant theory and representation theory that there are certain representations that are nice, and well, so the lattice point counting questions inside these vector spaces lead to results for number fields. Okay, and then finally, inductive methods, which really I'm just using as a catch-all for how to obtain old results from new. So there are a huge number of results here, and I'm going to describe just one example of them, which sort of represents the subject. Okay, so let me start off by talking about generator methods. And the idea is simple. So if you have a degree D number of fields, K over Q, then you look at the, any algebraic integer here, right? So the ring of integers is a nice degree D lattice. And well, the discriminant of the ring of integers, the discriminant of the number of fields, is closely related to the covolume of that. And so basically, you just compute the discriminant of this ring Z adjoin alpha. Z adjoin this one generator you picked out, which is going to be, well, it's going to be either equal to the discriminant of the number of fields or larger by a factor of a square. Okay, and Schmidt used this idea and I want to present his proof. To prove, one of the earliest results in the subject is that we have nd of x is less than x to the d plus 2 over 4. So it's conjectured the nd of x is less than x for each number field. And here we get an exponent that's linear in D. Okay, so this will be the only proof that I'll present essentially completely, but it's kind of worth thinking about. How do you get any upper bound at all? Well, here's how it's done. Okay, so first of all, so use the geometry of numbers. So the ring of integers can be embedded into d-dimensional Euclidean space, and there's going to exist some algebraic integer whose Archimedean embeddings are all small, and in particular bounded by a power of the discriminant. Okay, and don't worry so much about this trace 0 thing. It makes the proof a bit nicer, but essentially the second condition is what's important. Okay, so we're going to assume that this alpha that you happened to pick out generates the whole number field. This is not guaranteed to happen, but the case where it doesn't is easy enough to work around. Okay, so the minimal polynomial of alpha looks like this. So it's some polynomial with integer coefficients. Okay, and then the point is that so the Archimedean, so the coefficients of the minimal polynomial are going to be bounded in terms of the Archimedean embeddings of alpha, because they're because they're symmetric polynomials in it. And so you have these bounds, and you put these bounds together, you have an upper bound on the total number of minimal polynomials that could occur in this construction. And well, since the minimal polynomial determines the number field, if you want to bound the number of number fields, you just count all the possible minimal polynomials given to you by this construction, and you just add these exponents that occur in the disk K, and you get the Schmidt bound straight away. Okay, so this is the first proof in some sense in the subject, not chronologically, but perhaps logically. And I'd say, if you remember nothing, if you don't remember any other details from this talk, I'd ask you to sort of take away this proof, because this is in particular what Robert and I built upon. Okay, but before I say what it is we did, let me say a little bit about a few other methods. So Abelian methods. Well, if you want to count Abelian extensions, so let me not say too much about the details of these, but we can, we have two very powerful tools for enumerating them: class field theory and Kummer theory. Let me not delve into this so much, but let me just say that one can get, for example, if you want to enumerate all cyclic extensions of Q, well, you can do much better than to just get asymptotics, which is what we have on the bottom. So you can write down a very explicit and simple Euler product, which just tells you the discriminant of every possible such field and with what multiplicity it occurs. Okay, and when you're counting number field extensions that are not abelian, you quickly lose all hope of proving any simple formula like this. But cyclic cubic extensions, you have a formula like this. And in the general abelian case, you have, once again, it's a finite sum of Euler products, although in the general case, it takes a fair bit of work to compute explicitly. But still, I would say that the Abelian case is completely understood, or almost completely understood. Okay, so let me say about the parametrization method now. There are many people who've worked on this, but Bhargava is the most well-known, who's proved the most spectacular results. And here's an example of what he's proved. So he's proved that there's an explicit discriminant preserving bijection between the following two sets. Okay, so you have with this 12-dimensional lattice together with the z points of a nice algebraic group. Okay, so basically integral ternary quadratic forms, or quartic forms, excuse me. And essentially this is counting quartic rings, which is any ring, commutative ring, which is free of rank 4 as a Z module. And so morally, you should think of the second one as being just quartic rings, but it turns out then the bijection doesn't quite work. And in fact, there had been some previous work of Wright and Yukie along the subject. It turns out that if you want an exact bijection, then you need to count quartic rings together with a little bit of extra structure, and then you get it on the nose. And so you can count quartic rings, and so, well, if you count those quartic rings, which are, you want them to be integral domains, and you want them to be maximal, then you are counting the maximal orders of quartic fields. And so you have a lattice point counting question, which eventually leads you to counting quartic fields. And just to put this theorem in context, basically you have a bijection between GZ orbits on some finite dimensional lattice, where G is an algebraic group that has a representation on this V which is nice from the standpoint of invariant theory and representation theory, and then some kind of nice arithmetic objects. Okay, and so if you want to follow in Bhargava's footsteps, all right, so you go back and you read old papers in representation theory, invariant theory, commutative algebra, such as Sato and Kimura's work on the classification of prehomogeneous vector spaces. Okay, so you read these and you find some representation that looks promising, and you try and prove a parametrization theorem, and you hope to get lucky. And the good news is that for certain families of representations, you often do get lucky. So this is how we count number fields. This is also how Bhargava and Shankar counted the ranks on average of elliptic curves, proved that those were bounded. And so in cases where this works, it works absolutely brilliantly. But what one can't do is one can't reverse engineer it. You know, one can't say, I'm going to count degree 6 number fields. What representation gives it to me? As of now, there's just no way to solve the problem in this direction. Instead, one has to start with the representation theory and see where it leads. Okay, but this can be used to prove, among many other things, so counting results for cubic, quartic, and quintic fields. So we have asymptotic estimates for all of these. Each of them, in fact, we now have power-saving error terms, and in the cubic case, a lower order secondary term as well. So when the representation theory works, it works because we've turned these into lattice point counting problems, and we can bring the full force of analytic number theory to bear on these questions. Okay, so finally, I want to say a little bit about inductive methods. And really, when I say inductive, like I just mean any way of getting new results from old. So for example, counting solvable extensions or semi-direct products, any results of this nature, of which there are a large amount, or direct products also. So the following is the PhD thesis of Zhuyo Wang, together with a technical improvement by myself, Masri Tsai and Wang. Namely, so we know how to count degree D SD extensions. Well, suppose you count the direct product of SD with some abelian group. So we know how to count SD extensions, and we know how to count A extensions. And it turns out usually if you take some random SD extension and some random abelian extension, then their compositum is going to be what you want to count, and we can count these. And the idea is that we know how to solve the two counting problems separately. Can we count them? Can we put them together? And this is what Wang did. Okay, and they're usually disjoint, and you have this transitivity of the discriminant-like relation. So essentially, you're counting pairs where you have an SD extension and an abelian extension. And if it wasn't for this red asterisk, then the question would be very easy. So you have some fudge factor that's divisible by the primes that are ramified in both K and L, and you have to control it. It doesn't happen too often, and this is kind of where the mess is in the paper in practice. But we bound the error terms and proved that this doesn't happen too often. So mostly her work alone. Okay, so that brings me to the new result. So this is joint work of Robert Lemke Oliver and myself. And this extends what Schmidt did. And we have an upper bound in d of x is less than x to the 1.6 times log of d squared. So if you remember, Schmidt's bound, so the exponent was linear in d. And so we've reduced this to log of d squared. Okay, and just to, the second theorem is the theorem of which the first is a consequence. So just to give you a sense of where this log d comes from. So basically you choose R and K, and I'm going to sketch the proof. So I'm going to tell you what R and K are. And you choose these parameters so that the binomial coefficient is larger than R times D. And if you do this, then you get a corresponding upper bound on the number of fields. Okay, and I'm going to sketch the proof. It'll be, I don't know, very, very hasty probably, but I hope you at least get an idea of why these binomial coefficients appear. Okay, so just to give credit to the people who've done previous work. So I mentioned Schmidt's work already. But I want to prominently mention Ellenberg and Venkatesh. So they proved this bound that's, so this was the first bound that was sublinear in the exponent. And I want to mention this especially because, so we build directly on their proof. So our strategy is their strategy. And it's essentially an optimized version of their strategy. And there's also this work of Couvain's in 2019 that did get something. So he got log d cubed, and this was partially independent of our work, although his did come first, and we did use one of his key ideas, but a similar sort of idea. Also building on Ellenberg and Venkatesh. Okay, so what's the idea, right? So I've got about 5 minutes left. So what did Schmidt do? So he counted minimal polynomials. And another way to think of these, as we described before, you pick some element of the ring of integers of a number of fields, and you look at its symmetric functions, right? And well, you know the symmetric functions, then well, you can write down the minimal polynomial. And well, if you know the minimal polynomial of some alpha, then well, tautologically that determines the number of field k. Specifically, you just take q join x modulo that polynomial, and that gives you your number field. Right, so the idea, both in our paper, but that was first introduced in Ellenberg Venkatesh, also used by Couvain's. So given some k that we want to count, so instead of a single alpha, we start with an R tuple of algebraic integers. And if you go back to here, this is this R. Okay, and so you pick non-negative integers, right? And what we're going to do, so instead of symmetric functions, we're going to look at multisymmetric functions. So you take these algebraic integers, and you raise each to some non-negative powers, and you take the trace of that. And so there's a typo in the slide here, which I apologize for. I don't mean to say that these are algebraic integers. I mean to say that they're rational integers. They're honest to God integers. Okay, so we start off with this R tuple. Okay, and we look at various, combinations of the i's, and we write down a bunch of integers. And the idea, which we want to make work, is, do these determine the number field? Okay, and the answer is not quite, but close enough, usually, that we're able to make this work. Okay, and here's our more specific goal. So we want to prove that if we choose at least RD tuples, then the mixed traces usually more or less determine the number field, by which I mean up to finitely many options. And so, I mean, if you kind of look at this closely, so RD is the minimum that we feel like we should be able to get away with, because so what we have is we have R algebraic integers, each of which has D embeddings. And so you can think of this alpha 1 through alpha R. So this tuple lives in an RD dimensional real vector space. And we kind of take these and combine them, and we take a trace. And so the question is, can we recover an element of this RD vector space? Well, the best we could hope for is that we can do this if we have R times D pieces of data. And this is what we achieve, namely, and we do it with the i's essentially minimized. And if you go back to our theorem, so in most cases, this greater than is actually an equality, but this binomial coefficient on the left is going to be the total degrees of all the multisymmetric functions, namely the sum of the i's. And so to finish off the proof, okay, so we achieve this using essentially minimal i's. So this was, what I'm saying the least about, but the trickiest part of our proof. We end up using a theorem in algebraic geometry due to Alexander Hershowitz. So Couvain's was the first to introduce this. Okay, and then, well, if k has degree d and certain discriminant, then k has an integral basis whose Archimedeans are all small. This is more Minkowski style geometry of numbers. And therefore k is counted by some set of integer mixed traces, which we can bound. And then following Schmidt's idea, we're able to complete the proof. Okay, so this finishes my talk. Thank you very much.
Okay, thank you. Let's thank Ton. Are there any questions or comments? I suppose people can unmute themselves.
Hi. Could you say something about woods? You mentioned woods when you spoke on the Abelian method, the second method. Could you say something more about that, please? Thank you.
Yes. Where was it? Okay. I mean, so the idea is, basically you want to count these, to count these extensions, you want to count index D quotients. And really, what Wood did, and as far as I know, it's the only, actually, no, that's not true. So Wright's paper is, so David Wright was the first to, well, and also Maki, but his paper is a little bit hard to access, but they proved this finite sum of Euler products, and their treatment is a little bit complicated. So what Wood does in this case is really you're counting quotients of ray class groups, which is best done in the idyllic formulation, and she gives, I think, the simplest account of how to set this up. And so essentially you're counting quotients of ideal class groups. And I'm not sure if that's your question, but go ahead.
Okay, thank you very much.
Yeah.
Okay. Well, if there are no further questions, let's thank Frank Thorne again. Thank you.
Thank you, Dr. Thorne and Dr. Kakte. Participants, please note, the next session is the 15th plenary talk by Dr. Kannan Soundararajan. It will start at 7:45 p.m. Indian time. Participants may log in using the link provided in the email. Thank you.